Welcome back. We are already discussing various forecasting models for the supply chain decision making. We have discussed so far different types of time series methods in which we have studied the weighted moving average methods, and then we also realized that there are certain problems with those moving average methods, and as a result of that we discussed about the smoothing methods and we discussed exponential smoothing methods for helping us with the problem of excessive data and how we can handle the fluctuations which are happening in the most recent periods. In our earlier classes we discussed about simple exponential method, and now today we are going to discuss a complex exponential smoothing method where we have some kind of seasonality, and that seasonality we are assuming is of ratio seasonality type. Now in our earlier two cases we have discussed the basic exponential smoothing model where there is no trend, no seasonality. Then we also discussed a case of linear trend exponential smoothing model, and now we are moving to the third category of exponential smoothing models, that is the ratio seasonality model. Now to understand this model we have some hypothetical data available with us, and with the help of this data we will see that how this ratio seasonality model can be operated. Now the point of sales data which is available with us from January 2016 to July 2017, this is the actual demand. This is the actual demand, and in our notations this actual demand is represented as dt, that is the actual demand which is shown in the second column of this table. Now as we have discussed in our last two classes that demand is considered to be fluctuating around a base value. So in case of a seasonal factor also there is a kind of seasonality effect, and actually the demand is fluctuating around these base values. So we will determine these base values which is rather a more smoothened curve, and actually the demand is represented by this zigzag curve which is the fluctuation around this base value. So the third column of this table represents that base value. Now for the purpose of our understanding we have just assumed the base value of December 2016 to be 30, and the further calculation is shown here, and since we are talking of 2017 only, so there is no need for the base value of this period. Now since we already have assumed that this type of demand data has some kind of seasonality, so in this particular case we are aware that seasonality is there. So whenever seasonality is there, we need to deseasonalize the demand. And for deseasonalization purpose we need to divide the demand of individual periods. By the average demand of 2016. So if you see the average demand of 2016 is 24.07, that is the 24.207 that we get by summing the demand from January 2016 to December 2016 divided by 12, and you get the average demand as 24.07. Then for deseasonalization purpose we need to divide the demand of individual period by this average demand. So for the case of January 2016 we divided 19.36 by this 19.36 which is the actual demand of January by the average demand of 2016, and you get the seasonal index, and by doing this calculation you have the seasonal index of all the periods of 2016. For each month of 2016 you have this seasonal index. So the calculation is very simple, 19.36 divided by the average demand of 2016, that is 24.07, you get 0.804. Similarly, 25.45 divided by the average demand, you get 1.057, and so on for rest of the periods of 2016, that 19.73 divided by average demand of 2016, and you get the seasonal index. So now when you multiply the actual demand of these periods by the seasonal index, you get the deseasonalized demands. And this deseasonalized demand will be used for our calculation to get the forecast for any period of 2017. But here comes a question in our mind, that here I know that I am going to discuss a ratio seasonality model. So I know that the demand is seasonal in this case, but if you see this data, just 19.36, 25.45 and so on for entire 2016, it is very difficult from naked eye, that you can say that this is a seasonal demand data. It is almost impossible for any human being, just by observing this data, you can say that this is a seasonal demand data. So how do you need to have a deseasonalized demand, or what is the need of calculation of seasonal index? Since I am saying in this particular case, you know that we need to calculate seasonal index, we need to determine deseasonalized demand, but actually in reality, because of our inability, just by observing, if it is a very clear pattern, like if it is 19, 19, 19, 19, and then in the month of May, June, July, demand increases to 40, 45, 50, and then again demand comes to 20, 25, like that. So you can even by naked eye say that demand has a kind of seasonality factor. It increases to a very high level in a particular period and then it decreases. But here in this particular case, the data 19, 25, 19, 21, 20, 25, 23, 28, 26, 25, the data is so closely linked for each consecutive period that this seasonality is not visible just by observation. So how do we decide? Whether we are doing a right kind of thing? And the second thing, here I am saying that we are discussing the ratio seasonality model. Now how do I say that this is a ratio seasonality model? Why not it is a linear seasonality model? That is also a question. So for this purpose, we must know whether we are applying the correct model or not, and for that purpose we need to know about the forecasting errors. Forecasting errors will help us to determine whether we are using the right model or not, and for that purpose we will discuss briefly, not in much detail, about some of the possible errors which are there in the forecasting and what are the measures we use for the forecasting errors. So in case of forecasting errors, we all know that forecasts are the tentative values for the future, and the actual demand like this and the forecast which we have not given. So let us say for the January 2016, if I am forecasting in December 2015, so forecast can be, let us say, 21, but the actual demand is 19.36. So the difference of actual demand and the forecasted value is known as the forecasting error. So forecasting error, let us represent for a particular period as ET. ET is the difference of demand and forecast for the same period. So, the difference of demand value and the forecasted value for a particular period is known as forecasting error. This is very simple, no complication, but this measure alone is of limited use. This definition of forecasting error has limited application. So, we have developed certain other measures of forecasting error, and now we are going to discuss those other measures of the forecasting errors. The other measures of forecasting error, the simplest one is average error. That is the simplest one, and the average error is defined as the average of forecasting error. Like in this particular case, you have forecasting error for January, February, March, April, May, June, July, and let us say if in the month of December I am calculating what is my average forecasting error. So, that is the average of forecasting error for n number of period. So, if I am doing forecast for n number of periods, so the average of errors for these n number of period is my average forecasting error. It is normally assumed, or it should be, for a large sample size the forecasting error should be 0 or should be very close to 0. But it is also possible, we all know, that for one period there is a problem with average. We all know that it is possible that for one period the error is plus 10 and for other period the forecasting error is minus 10. So, if I take the average of these two forecasting errors, so plus 10 and minus 10, the average error will be 0. But in both the cases, in both these periods, the forecasting error is individually very high, but the average error will be 0. What I am trying to say, that E January is plus 10 and E February is minus 10. So, if I am taking the average of these two periods, that will be E January plus E February divided by 2, and plus 10 minus 10 divided by 2 will be 0. So, by definition it looks that average error is 0. So, I am having a very good forecast, but actually because of different signs of these forecasting errors I am getting the 0 forecasting error. But nevertheless, in a large sample it is assumed that there will be certain plus values and there will be some negative values, and with the positive and negative values you should have a 0 average error. So, that is what we expect. Now, as we have discussed that there is a natural limitation of average value, and this is not only in the case of forecasting errors. The problem of average is always there, that because of the sign you will have this type of issue. So, there is a second measure of forecasting error which is known as mean absolute deviation, very popularly known as MAD. MAD is a very popular measure of forecasting error. To eliminate the problem of the sign in the forecasting error, now we take the absolute values of error to calculate the mean absolute deviation. So, it remains like that only, that you are calculating the average, but the average is of absolute values. You take the absolute values and then you determine the average of that. So, whether it is plus 10 or minus 10, if I am calculating mean absolute deviation, it will be absolute values and you get the tan as mean absolute deviation. So, for same values we just saw that the average error was 0, but mean absolute deviation is 10. So, mean absolute deviation is a very popular measure of forecasting error, and this mean absolute deviation helps us in determining whether we have taken a correct forecasting model or not, whether we are considering ratio seasonality it is appropriate or not. If my MAD values are higher, then my model is not appropriate. Some other model may be more suitable in my data. So, with different types of models, I will calculate the MAD value, and whichever model will give me minimum values of MAD, I will select that model for my forecasting purpose. And at the same time, let me also tell you about the smoothing constants. In our last classes, we have discussed about the use of smoothing constants. We will use three types of smoothing constants: alpha, beta and gamma. Alpha for smoothing the fluctuations of the base, beta for smoothing the fluctuations of the trend, and gamma for smoothing the fluctuations of the seasonality components. So, what should be the correct value, or what should be the most appropriate values of alpha, beta and gamma, that also can be checked, then that also can be realized using this mean absolute deviation, because the selection or to take a particular value of alpha, beta, gamma, there is no mathematical calculation, there is no formula. Just by observation, just by practice, we take alpha, beta, gamma. The thumb rule we have already discussed in our earlier class, that the smaller values of alpha, beta, gamma, the values of alpha, beta, gamma we discuss varies from 0 to 1. The smaller values of alpha, beta, gamma, these values have more smoothing effect, but in case there is a quantum jump and we want to have a different base or a different level of trend or a different level of seasonality, then you take higher values of alpha, beta, gamma. The smaller values of alpha, beta, gamma gives more smoothing effect. So, that is the thumb rule, but as we know that alpha, beta, gamma normally should be between 0.05 to 0.30, though values can lie from 0 to 1, but in most practical purposes alpha, beta, gamma varies from 0.05 to 0.30. So, what should be the appropriate value of alpha, beta, gamma? In my case, for that also we take the help of mean absolute deviation, and by putting different values of alpha, beta, gamma, you calculate the MAD values, and whichever values of whichever set of value give you minimum values of MAD, that is your selected value of alpha, beta, gamma for a particular set of data, for a particular case of forecasting. Then there is one more method also, one more measure of forecasting error also available to us, that is mean squared error, and it is abbreviated as MSE, mean squared error. In mean squared error, you take the square of forecasting errors and then you take the average of those forecasting square. The purpose of MSE, because of this square factor, the purpose of MSE to penalize the very high forecasting errors. So, in case because of square effect, if there is a higher forecasting error, by square of that term it becomes even higher and it immediately comes to know that there is a particular set, there is a particular case of data where the forecasting error is very high. So, this gives you additional information other than MAD, but not very popular in use, but can be used in combination with MAD. Then where one more forecasting error measure is there, that is known as mean absolute percentage error, which stands for MAPE, mean absolute percentage error. Now, mean absolute percentage error is one more additional measure of forecasting error, in which what we are doing, we see that how much the forecasting error is an offset of our actual demand, and that is determined by this method, and then you take the average. So, this is one more measure of forecasting error, but out of these four, the most popular is mean absolute deviation, and with the help of this mean absolute deviation, we will determine that which method to use and which method is more suitable, what are the values of alpha, beta, gamma which are suitable for our particular case. So, now we are not doing all these calculation for this given set of data. We assume that ratio seasonality is best suited for this particular case. So, but otherwise in all practical cases we need to do the calculation of mean absolute deviation, and once we have done this calculation of mean absolute deviation, then only we can determine that this model is suitable or these values are suitable. Now, let us see, once we have assumed that ratio seasonality is best suited for this particular case, so then we go for deseasonalization, as we have already discussed, by dividing the actual demand by the average demand of a particular period, and then we determine the seasonal index of different periods. Once we have determined the seasonal index, and since it is a ratio seasonality model under the case of exponential smoothing, so we need to see how to determine the forecast, and since it is a ratio seasonality case, so now we will go in the reverse direction. Like, I have the actual demand up to July 17 and I want to determine what will be the forecast for August 2017. So, now in case of a ratio seasonality model, in case of ratio seasonality, when I want to calculate the forecast for August 2017, I will use the most recent base. The most recent base is of July 2017. That is the most recent base of July 2017, and I will multiply, since it is a case of ratio seasonality, so actually this base gives me deseasonalized demand, deseasonalized forecast you can say, and then I want the forecast of August 2017. So, I will multiply this deseasonalized forecast with the seasonal factor of August 2016. So, that is 1.178. So, I will multiply this by the seasonal index of August 2016. Now, my job here is to determine the values of base of 2017. So, I have the base of June 2017, I will use these values of 30.0273 to get my updated base for July 2017. And already, since I have just started this problem, so because of my initial calculation, I have the seasonal factor for August 2016. But this seasonal factor of August 2016 will also be used to get the updated seasonal factor for August 2017, and that August 2017 seasonal factor will be used for calculating or for determining the forecast for August 2018. So, the point which I am trying to make, seasonal factor will be used for the previous years and the base is used of the current years. So, if I want to write this equation, in a generic term, the equation will become like the FT1, the period current, and one period ahead, that signifies FT1. So, if today I am in July 2017, FT1 means it is August 2017. Then July 2017 is my current base, multiplied by I August 2016. So, August 2016 will be when I am in July 2017. So, if this is a data which is presented on monthly basis, this data is present on monthly basis, you may have data presented on the quarterly basis, you may have data presented on the half yearly basis also. Here the data is presented on the monthly basis. So, you have 12 months in a cycle. So, if I am in July 2017, one cycle is of 12 months and cycle is represented by capital L in our case. So, if I am writing T minus L here, it means it is July 2017, it becomes July 2016, and I want the base value of August 2016. So, plus 1. This makes my this equation into the general form. When I want to determine the forecast for the next month, in case of when today I am in July 2017, if today I am in July 2017 and I want to determine the forecast for August 2017, this is how I will write the equation. And if I want to use this formula, if today it is July 17, so this is for August 2017. Now, I want to determine, if today again I am in July 2017, but now I want to determine the forecast for December 2017. If I want to determine the forecast for December 2017 or for any other month, October, November, December, etc. So, in that case, I write that I want to determine the forecast of M period ahead, and that will be ST, that is the base of July 2017, multiplied by I T minus L plus M. That signifies that I want to determine the forecast of MH period from the current period. So, with this we get the most generalized forecast using the current base and the seasonal index which are available to us at the moment. So, we will see now in our next class that how to calculate this updated base value and how to calculate this updated seasonal index, and then how to determine the forecast for the any next period in case of ratio seasonality model. Thank you very much.